In this video we study a famous problem in distributed systems called Byzantine agreement. Roughly speaking, the goal is to reach agreement among a set of distributed parties, which we call nodes. In the example here, we have 4 nodes, each with its own numerical input. We want to find a distributed protocol that makes it possible for the nodes to agree on a single value. More formally, we want to solve the so-called consensus problem. An algorithm is said to solve the consensus problem if it has the following properties. The first property is called agreement, which says that all nodes must decide on the same value at the end of the execution of the algorithm. The second property is called validity. The validity property requires that, if all correct nodes start with the same input value, then the correct nodes must decide on exactly this input value. Lastly, the third property is called termination, which says that all nodes must eventually decide on a value. The consensus problem is challenging if nodes may fail during the execution of the protocol. In the worst case, a failed node doesn't just disappear. It may still send arbitrary, possibly nonsensical or conflicting messages around. It is also possible that such a node has been corrupted and acts maliciously, trying to prevent the other nodes from reaching agreement. We call a node that exhibits such worst-case behavior a Byzantine node. In the example here, the node in the bottom left is such a node. Let's assume that it must send some message to all other nodes according to the protocol. However, the node only sends the message to one node and drops the other messages. Alternatively, it may modify the messages and send these altered messages, which are not in agreement with the protocol. It is not hard to believe that such worst-case failures make it harder for the correct nodes to reach agreement, as they do not know which nodes are correct and which ones are not. The consensus problem with Byzantine nodes is often called the Byzantine agreement problem. Is it even possible to solve the Byzantine agreement problem at all? We now show that the answer is yes. In order to keep things simple, we focus on the case where there is exactly one node that exhibits Byzantine behavior. Concretely, we discuss a fairly simple protocol that lets all correct nodes agree even in the presence of one misbehaving node. In the first round, every node sends its local value to all other nodes. Note that the Byzantine node X sends 3 different values in this example. It sends the value 1 to node U, the value 2 to node V, and the value 3 to node W. Once the messages have been received, each node puts the received values into a set, also storing the information from which node it received the value. As we can see here, each node receives messages from a different set of nodes, and each set contains a different value for node X. In the second round, each node sends its collected set to all other nodes. As before, node X may choose to send different sets to the correct nodes. Once these messages have arrived, each node has the sets of other nodes in addition to its own set. Note that node X could also choose not to send any set. In other words, any of the sets that node X sent may be empty. Let's rearrange the information so that we can reason more easily about the information available at each node. We can ask ourselves, which value has been seen at least twice associated with the same sending node? Since each node has the sets SU, SV, and SW locally available, it is easy to see that each of the 3 correct nodes receives the pairs U12, V9, and W19 twice. So, if we put all such pairs into a set T, we conclude that all correct nodes have exactly the same set T. In the example here, the values from the Byzantine node are ignored because they are all different. Now, given that all correct nodes derive the same set T, how can they use this set to reach a decision? For that, we introduce the following rule. Do all nodes have different values in T? If this is the case, decide on the smallest value in T. If this is not the case, decide on the smallest value that occurs at least twice. Let's consider what happens in our example. All values in set T are different, so all correct nodes decide on value 9, the smallest value in the set. Okay, agreement was reached in this example, but why does this protocol always guarantee agreement? If the correct nodes always have the same set T, they will clearly decide on the same value if the decision only depends on set T. So, why is the set T always the same at all correct nodes? The value of a correct node is always received at least twice, once from that correct node itself and once from another correct node. So, every correct node puts the value of the other correct nodes into set T. What about the value of node X? We saw in the example that the value is ignored if node X sends a different value to each correct node. However, if it sends the same value to at least two correct nodes, these nodes will send the value around and this value will be added to T as well. Note that node X cannot get another value into T because there are only three correct nodes. We can conclude that the protocol has the agreement property. What about termination? Is it guaranteed that the protocol execution will halt? The answer is yes. The protocol consists of exactly 2 rounds after which every correct node decides. In other words, there are no loops and so it holds trivially that the execution always terminates. What about validity? We need to show that, if all correct nodes start with the same input value, then they will decide on this value. In this case, every correct node receives the input value at least 3 times. If the value of node X is different, it may be added to T as well, but it is the only node with this value. Now we see the reason for the complex rule that specifies how we determine what value to decide on. The correct node's input value appears more than once in T, and it is the only value that appears more than once, so all correct nodes agree on this value as desired. This proves that our protocol is correct if there is a single node that exhibits Byzantine behavior and 3 correct nodes. Note that the idea of this algorithm can be generalized for any number of failures. If every node always broadcasts all information it has learned so far in f+1 rounds, consensus can be reached if there are at most f failures. The disadvantage of this algorithm is that the message size grows exponentially with the number of failures. Coming back to our algorithm that can handle one Byzantine failure, does it still work if there are only 2 correct nodes? Well, in this case, we have a problem. Let's assume that the correct node, U, has the input value 0 and the correct node W has the input value 1. The Byzantine node X could send value 0 to U and value 1 to W. Node U sees that 2 nodes, node X and itself, have value 0. Since these 2 nodes may be the correct nodes, node U must decide on value 0, otherwise it would violate the validity property. However, node W sees that there are 2 nodes with value 1. For the same reason, node W must decide on value 1, which means that no agreement is reached. We conclude that Byzantine agreement cannot be solved if there are 3 nodes in total and one of those nodes may exhibit Byzantine behavior. We can easily generalize this result. Let's assume that there are n nodes with 1/3 of the nodes being faulty and 2/3 of the nodes being correct. Half of the correct nodes have the input value 0, and the other half have the input value 1. If the faulty nodes claim that their input value is 0 in their messages to the correct nodes with input value 0 but send the value 1 to the correct nodes that have input value 1, we have exactly the same situation as we had with 3 nodes. The correct nodes with input value 0 must decide 0 and the correct nodes with input value 1 must decide 1, otherwise they would violate the validity condition. It follows that there is no solution to the Byzantine agreement problem if at least 1/3 of the nodes may be faulty unless some additional assumptions are made. For example, this bound on the number of Byzantine nodes does not apply if the nodes can generate proof that Byzantine nodes sent around inconsistent information. If all messages are signed, it suffices to collect 2 conflicting messages from a Byzantine node to prove that this node did not adhere to the protocol. When the nodes have such proof, they can ignore the offending node to make progress in their protocol execution. Let's summarize what we've learnt. We discussed the Byzantine agreement problem, which is the consensus problem with worst-case failures. We showed that the Byzantine agreement problem can be solved by looking at a simple protocol that works with 1 faulty node and 3 correct nodes. We further showed that the problem cannot be solved if 1/3 or more of all the nodes may deviate from the protocol in arbitrary ways, so 3 correct nodes are required if there is 1 node that exhibits Byzantine behavior. Thanks for watching.